Hey there, geometry. Today we're going to dive a little more deeply into what it means for figures to be similar. We're going to talk about the properties of similarity and also focus on circles and finally triangles. That's the goal here, is to get back to triangles and to decide when things are similar. Now, with lesson 12 and 13, we didn't really talk about triangles, and that was on purpose. We were trying to just make sure that you guys understood that similarity can be similarity of anything, not just triangles, not just straight-edged pieces, which was sort of fun. If you look through the problem set that was actually assigned, or the problem set that was available for 12 and 13, you'll see that there was a teapot and a lot of other things. So we're going to shift back into triangles in a little bit and sort of tie everything together. So first of all, we said that for a figure A in the plane, it must be true that A is similar to A. Let's describe why that must be true, and we're going to describe why that must be true with some pictures, because that makes sense, right? I should point out a very important fact that by just saying it, I assumed you knew, but you don't yet, because I haven't taught it to you, or you do, and I don't know, whatever. Let's just say that this symbol right here, okay, that little squiggly, denotes similarity, okay, where this denotes equality, this denotes congruence. That squiggly right there denotes similarity. So when I say A similar to A, that's what I meant. Okay, so for this one, I just drew a simple triangle so we could actually talk about it. Is the figure similar to itself? Okay, think about that for a second, and we'll answer at the end. We'll move on. But we said that for figure A in the plane, it must be true that A is similar to A. Describe why this must be true. So I drew a figure A. Is the figure similar to itself? Okay, waiting. Let's move on to the next one. All right, example 2. We said that for figures A and B in the plane, so that A is similar to B, then it must be true that B is similar to A. Describe why this must be true. I have some triangles here. I copied and pasted triangle A from the previous slide, and then we have triangle B here. So if we say that A is similar to B, can we say that B is similar to A? Okay, think about it, and we're moving on. Okay, what about this one? So for figures A, B, and C in the plane, do you believe that if A is similar to B and B is similar to C, then A is similar to C? Okay, I'm not going to give you 3 more triangles. We're just going to talk about it. So, for example 1, yes, A is similar to A. If you remember in previous lessons, we talked about a scale factor could be 1 for a dilation, as long as the sides of the figure are proportional, then the figures are similar, if not congruent. In this case, they would be congruent, and if they're congruent, they're also similar. If something is congruent, it is similar. If something is similar, it is not necessarily congruent. Okay, for example 2, yes, A is similar to B, therefore B is similar to A. Remember, we can scale things up and scale things back down. Your scale factor would be less than 1 if it goes down, and then flip it over greater than 1 if it goes back up. And if you multiply your 2 scale factors, you would get 1. And then 3, yes, if A is similar to B and B is similar to C, then A would be similar to C. Again, you would multiply your scale factor, so you'd have a scale factor of 1 if there's dilation, scale factor 2, a scale factor 3, and the scale factors would work like, that's not a 3, would work like that. Okay, let's explain one more way. Give me a new slide. Okay, let's explain one more. If I was doing A being similar to A, what are some transformations that would map A to A? Well, if I had a rotation with a degree of 0 or even 360, that would map A to A. How about a reflection? I mean, say if our triangle looked like this, it was an isosceles triangle or even an equilateral triangle, and I reflected it along a line in the center, that would be a mapping to A. Or even a translation. Can't spell. Translation. With a vector length of 0, which is sort of funny, but that would map A to A. A dilation with a scale factor of 1 would map A to A. So A would map to A. A is similar to A. We called this reflexive a long time ago, when every figure is similar to itself. You can just flip it back and forth, right? How about A similar to B, B similar to A? Okay, this one's a little bit easier to discuss. Anything that maps A to B, A to B can be undone and map B back to A. Okay, be it a rotation, we could always rotate it back. A reflection, we can always reflect it back. Even a dilation, we can always dilate it back. I can't think of anything else. Everything can be undone when we're talking about transformations. And this is sort of our transitive property. And then the last one, A is similar to B, B is similar to C, and C is similar to A. Well, let's write that the right way. Therefore, A is similar to C. Okay, this one makes total sense also. I mean, same explanation as A being similar to B. Everything can be undone. Oops. Undone. That's our composition transformations. And this would also be the transitive property. Okay, let's talk circles. Based on the definition of similar, how would you say that two circles are similar? Okay, I mean, if we look at two circles, those circles are so excellent. We've got circle A and circle B. All right, so if we have two circles with the same radius, different centers, they are equal. We know that, let me get a different color here. So I'm looking at circle A and circle C. Radius 1 is equal to radius 3. Therefore, I can translate it along a vector and map circle A to circle C. So similar, these are actually congruent. And therefore similar. Okay, if two circles have the same center, different radius, say radii, I can dilate them. So if we have we have radius 1. That's awesome. And then I have radius 2. Okay, circle, let's say circle D has radius 1 and circle E has radius 2. I can dilate those two circles to make them equal. So they are similar. My scale factor, say I'm going from 1 to 2, my scale factor, this is really important, would actually be, if I'm getting bigger, radius 1 divided by radius 2. And that would be my scale factor. That is an important notation to remember. Okay? So, let's get another slide. If you have circles with different centers and different radii, they can also be similar. Okay, on the previous slide I had these drawn out, but that's okay. I can dilate them to get them back to the same radius, dilate, and then translate along a vector. So first my scale factor, if I'm going from A to B, my scale factor would be getting bigger, so again I would divide radius 2 by radius 1. Let's just do that to make our notation the same. And then I would translate along a vector. And they would be back mapped onto themselves. Here's a really good example of two circles that if I just dilated them, I would map one onto another. So this would be dilation only. Okay, no translation would be needed, just dilation, and I would get one circle mapped onto another. Okay, pretty cool. Okay, let's touch just a little bit on triangles and similarity of the triangles. I can say that triangle ABC is similar to, so we have right here, triangle DEF. Okay? That means that there is a similarity transformation that maps triangle ABC to triangle DEF. So that similarity transformation takes A to D, B to E, and C to F in the correct order. So when we see triangle ABC is similar to triangle DEF, we know that there's a correspondence. So angles are equal. And angle C, okay, get my measurement symbol in there. So the measurement of all the angles are equal. That's our correspondence that is existing. So the angles are equal, and then the sides are still proportional. They're not equal because it's just similar, it's not congruent. So I can say that DE over AB, that's going to give me a scale factor, right? is equal to EF over BC is equal to DF over AC. That's going to be my scale factor. All right, we just did a proof in a non-proof way, but I know you guys understand it. So that really is our theorem of similar triangles, if I could spell. Triangle, oh my goodness. Triangles. That's a T and an R. All right, let's move on. Example 4. So suppose triangle ABC and triangle DEF are corresponding, are related, and that under this correspondence, corresponding angles are equal and corresponding sides are proportional. Does this guarantee that triangle ABC and triangle DEF are similar? Yeah, we just talked about it. Now we're sort of doing the backwards. So I didn't tell you that these are similar. We did not say that ABC, triangle ABC is similar to triangle DEF. What we said was angles are congruent or equal and sides are proportional. Therefore, the triangles are similar. That is our converse of the previous theorem. No problem. Example 5. So the intent of this example is to highlight how an efficient sequence of transformations can be found. Like it can be efficient to map one figure onto its similar image. And there are sequences that we can just list out to make it super simple. So let's talk about it. In the diagram below, triangle ABC and triangle A prime, B prime, C prime are similar. Describe a similarity transformation that maps one onto another. Okay? We could describe this in any order we wanted. We sort of do the dilation first. So first I could dilate my similar triangle with a scale factor bigger than 1 to get it back to ABC, correct? And then I think I need a reflection because they're not in the right order. And then probably a translation. And finally, a rotation. You can do those in any order that makes sense to you. I would probably put the rotation pretty early because my mind likes to see things in the right order before I start reflecting or translating. But that would be a similarity transformation that would map one thing to another. Okay, part B says, Joel says the sequence must require a dilation and 3 rigid motions. But Sharon is sure there's a similarity transformation composed of just a dilation and 2 rigid motions. Who is right? I would say both. For instance, your reflection could account for the translation, depending on where the line of reflection is. Right? Okay, let's change to blue. If I reflected, somewhere in the middle, I could reflect one thing onto another and be done after I dilated it and rotated it. If I just look at a line and a line of equal length, if I wanted to reflect, let's say first, I would want to reflect over this line and then translate it to get there, I could. Or a line and a line. I could reflect it over the middle and not have to translate it at all. Cool? All right, lesson summary. That was a nice lesson. Similarity is reflexive because a figure is similar to itself, and similarity is symmetric because once a similarity transformation is determined to take a figure to another, there are inverse transformations that can take the figure back to the original. Okay? And then we also talked about the theorem of similar triangles. Awesome. Good job.